this lab is the AC circuits, AC series circuit lab. And of course we know about series. That's putting things in circuit elements in one after the other till you get back to where you started. That's a series. And so let's talk very briefly about what's going on here. So if we have a resistor, of course, we know that Ohm's law tells us what's going on in a resistor. And the question is, what goes on in a resistor when I put an AC input onto it? I mean, we talked about, and we did all kinds of experiments with DC voltages, and we know that resistors obey Ohm's law in DC. Well, turns out resistors obey the same law in AC very simply. So if you have a voltage that looks like this, an AC voltage, the question is, what does the current look like through a circuit with just a resistor in it, a pure resistor? And it turns out the current looks the same. In other words, the current and the voltage here are what we call in phase. There are 360 degrees in one cycle, 180 and 90 degrees in a quarter of a cycle. So what I'm talking about in phase means in the phase angle here. So they're in phase, they're synchronized, they're behaving exactly like a pure sine wave, the voltage and the current. I can see that by solving for the current for Ohm's law. Resistors simply resist, and so there's no funny business with regard to current and voltage with just a resistor. So the current and the voltage are in phase. If the current goes up, the voltage goes up. If the current goes to zero, the voltage goes to zero. The resistors simply resist. They're called passive circuit elements, basically, for that reason. They don't do anything interesting to the relationship between the voltage and the current through the circuit. And again, I encourage you to read over the details of the handout, which goes into great detail about what's going on when you put a capacitor and an inductor in a series circuit. So let's take a look. So in part one, we're going to have a resistor and a capacitor in the circuit. And so for capacitors, you know, it takes some time to charge and discharge a capacitor depending on the resistance involved. And so when you apply that to a voltage that looks like this, and you see there's some kind of a time lag between the voltage and how the current flows through the circuit, because the capacitor takes some time to charge up and discharge, it's going to change the phase relationship between the current and the voltage in a circuit. And if you do the calculations, go through the theory, you find out that a capacitor shifts the voltage and the current 90 degrees out of phase. Let me draw what's called a phase diagram. If we have a circuit with just a voltage source and a resistor, the voltage across the resistor and the current through the resistor are in phase, as we talked about. And so I'm going to call this a zero phase angle, a 0 degrees phase difference. And so when I plot the voltage across the resistor and so forth, there is no difference between the voltage across the resistor and the voltage that's being applied to the circuit, because they're in phase. And so I would plot that voltage in this direction. There's no phase difference between the voltage and the current in a resistor. And again, I'm skipping past a lot of the theory, which you should get into if you haven't gotten to Faraday's law and things like that in class. You'll have to sort of rely on just reading through that. So here's my phase diagram. It turns out that for capacitors, it's not so simple. And if you go through the analysis, you find out that the current and the voltage are 90 degrees out of phase. 90 degrees out of phase, and we represent that again by a phase diagram where this is 0 degrees phase and this is 90 degrees phase, and so the voltage that you measure across the capacitor is plotted in this direction. And again, I leave you to read through the theory there in the handout. And of course the voltage across the resistor is plotted in the 0 phase direction. So if you add, if you have a resistor and a capacitor in a circuit, so this is a symbol for an AC voltage source. If you have a resistor and a capacitor in a series circuit, this is an RC circuit, yes, but it's connected to a sinusoidal voltage supply, so it's a way different story. The capacitor, because it takes time to charge and discharge, desynchronizes the current and the voltage in that circuit. If you go through the theory, which is in the handout, you find that desynchronization is a 90-degree factor. So we plot the voltage across the capacitor, which is a pure capacitor. That is part A. You want to show that indeed the capacitor is made up of not a resistance wire. It doesn't have any resistance. It's just a place for charges to pile up on a plate. It doesn't have any inductance. We'll talk about inductors in a bit, because inductors are basically coils of wire. And there's no coil of wire inside a capacitor. It's simply two plates. One has positive charges on it, one has negative charges on it. So it doesn't have anything like inductance. It doesn't have anything like resistance. It's a pure circuit element. And the theory says the phase relationship is 90 degrees between the current through the resistor and the current through the capacitor. So if it turns out, because that's 90 degrees, we have a nice x, y coordinate system here, we can use the same mathematics as we use for vectors, which have x and y components. Voltage is not a vector, but voltage can be considered to be what's called a phasor in these more complicated circuits, where the voltage and the current have shifts in phase because of what they experience in the circuit. So in part A, we want to check out is a capacitor a pure capacitor? So we to get the answer to the total voltage across the circuit, we add them like vectors, because we're talking about this phase. So this is sort of a phase diagram in a way. And so the voltage across the resistor and the capacitor is, by Pythagoras' theorem, equal to the square root of the voltage across the resistor squared plus the voltage across the capacitor squared. And this phase angle here, you want to check with part A and see that, as far as you can tell, within your experimental error, which we need to talk about quite a little bit later, that angle is 90 degrees. Now, the story is not quite so simple, which is why we need to do this experiment and kind of talk about this for an inductor. The circuit symbol for an inductor is something like that. It's a coil of wire. In fact, inductors are often called coils for short. So this is the circuit symbol for an inductor. Inductors obey Faraday's law and Lenz's law, which is a whole story in itself, which you may not have gotten to in class. If you have, that's wonderful. If you haven't, we'll have to sort of defer the deep discussion of what's going on here to that time. But the point here in the lab is that there is a phase change when you have an inductor. If you have a pure inductor, the phase change turns out to be, again, go through the mathematics in the handout, the phase change is 90 degrees. So the voltage across an inductor compared to the voltage across a resistor in a series circuit is 90 degrees for a pure inductor. But unless you have a superconducting inductor, which has no resistance, that's what superconductors have, basically, no resistance, any real normal conductor is made up of a coil of wire which has lots of resistance. In fact, in the coils of wire that we have, the inductors we have, the resistance of the inductor is as big as the resistance of the resistor. They're both around 100 ohms, depending on which inductor and which resistor you have. So that means I don't draw the voltage across an inductor at 90 degrees this way. I draw it at some angle that's got a resistive component and an inductive component. So that's the goal of part B, is to find out what is this angle here that you draw the voltage across the inductor at in this phase diagram, where this is 0 phase and this is 90-degree phase also. So if the inductor has as much resistance as it has inductance, this angle is going to be, as you can probably expect, 45 degrees. And in fact, that's not too far away from the angle you're going to get for this inductor. The inductance depends on, well, here are a couple of formulas we need to talk about. The inductance, these are called inductive reactances and capacitive reactances. These inductors and capacitors are active circuit elements because they shift things around and they're active. They actively take some time to charge up for a capacitor, and they actively resist a change in the magnetic flux through the inductor. So and there's a minus sign involved there, which is called Lenz's law. So and this depends on, as you can imagine, the frequency. That is, if the voltage is changing really fast, then there's going to be a different effect on the current in these active circuit elements than if the voltage is changing rather slowly. So it turns out these are, this is the relationship between the angular frequency, omega equals 2 pi times the frequency. Our frequency, of course, is 60 hertz. That's 2 pi times 60, which is 377 radians per second. That's the angular frequency of the power at the power receptacles. And so that's what we're needing. So this is actually going to be 377 all the time. And this is the value of the inductance of the inductor. And for a capacitor, it's again, you have to go through the theory to see this, but that would take a long time, and you don't have a long time. You got to figure out how to do this lab. So this is the capacitive reactance, and this is the inductive reactance formulas. And again, you can see here that as the frequency increases, this gets smaller. That's interesting. And what that practically speaking means is, if you have a capacitor and you charge it up and discharge it really fast, it doesn't have much time to charge up and discharge, so it doesn't do much to the current. So we have an inverse relationship. The higher the frequency, the less of an effect, a blocking effect, the capacitor has on the circuit. And in terms of Faraday's law, it's the changing magnetic flux that gives you this term here. And if you have a circuit in which the voltage is changing faster, then of course the magnetic flux is also changing faster, and that increases the inductive reactance. So that's kind of the hand-waving explanation for why this is downstairs and why that's upstairs in these relationships. And again, there's nothing like that for resistors. It's just Ohm's law, V equals IR, and there's no omega factor, so to speak, for resistors. There is for an inductor and a capacitor, and for the reasons they're upstairs and downstairs, like I just mentioned. Okay, so in the second part of this experiment, we have to find this angle. Now, from practical experience of many years doing this lab, we can find that angle by a vector addition problem, but the easiest way to find that angle is by turning this into components. That is, this is the voltage across the inductance part of the inductor. This is the voltage across the resistance part of the inductor. And of course, you can't separate those. you can separate them mathematically, but you can't separate them in real world because an inductor has got resistance and inductance at the same time. And the inductance depends on the frequency, so it's rather more complicated. However, we know for a resistor, Ohm's law applies. And so we can calculate this. If we know the current, and the current in your experiment is going to be 100 or 150 milliamps, which is 0.1 amp. We know the current and we measure the resistor simply resists. So if this resistance is 100 ohms and the current through there is 1/10 of an amp, then 1/10 times 100 is 10. And you're going to see that that's about the case for your situation. That is, if you have a roughly 100 ohm resistor and 10 milliamps, the voltage drop across the resistance part of the inductor is a pure resistance, and it's going to be given by about 10 volts. Okay, so we can actually calculate that. And that's what you should do. Measure the resistance of the inductor. It doesn't change unless it gets a little warm, but we're going to not keep it on long enough to get warm. So we can use Ohm's law to figure out this value here by Ohm's law, and we can use this value that we measure from directly measuring the voltage across the inductor, that's what that is, to get this angle. So if we know the voltage across the inductor and we can calculate the voltage across the resistance part of the inductor, we've got it made because that's a right triangle, and V sub RL over V sub L is equal to the cosine of that angle. So that's how we get that angle in part B. And we're going to do this for two different currents, and the answer should be the same angle. It's the same inductor. It's got the same inductance, and it's got the same resistance, regardless of what current runs through it. And so it should be the same angle. So you're going to get two values for this angle, and I would average them to use that value in part C. Okay, so that's kind of running roughshod through the theory of capacitors and inductors in AC circuits. Again, the more elegant derivation is in your textbook, is also in the handout, and complete with every step. So let me talk a little bit more about this impedance diagram. And I have to beg your indulgence to tell a story. How do we figure out how to draw these things? Well, this is my mnemonic, Eli the Iceman. Now, you may find this hard to believe, but let me put this on tape for the record, that we had an ice box when I was a kid, and you put ice in it. That's how you keep things cold. And that's why your grandparents probably maybe still call them ice boxes, because that's what they were until the 1930s and 40s. So every week we would have ice delivery. We lived on the shores of Lake Michigan, so it was easy to get ice. Ice was cut up from the lake and stored for the whole year in ice storage facilities, and was delivered by Eli, the Iceman. Eli, the Iceman, had a horse which delivered our ice. So we had a wagon, we had an ice wagon, and Eli's horse, I don't know the name of Eli's horse, but the horse knew where to stop, who had ice boxes. So Eli would come once a week with his horse and stop in front of our house, and my mother would put out a sign that looked like this on the front window. And depending on how much ice you needed, if you needed 100 pounds of ice, she would hang it up with the 100 on the top. If you needed 50 pounds of ice, she would hang it up the other way. If you need 25 pounds or 75 pounds, she'd hang it up with those showing on top. So Eli knew without going in and knocking on the door how much ice we needed that week. And furthermore, if I was quick enough, I would get out the front door and I would have Eli chip a little piece of ice off this nice pure Lake Michigan ice, and I would get to suck on it before he brought it in the house in the kitchen. Of course, my folks had to pay for that, but that's okay. I got my treat. So this tells me which way is what in terms of my phase diagram. So I don't know if you've talked about EMFs yet, but EMFs are just voltages, or a form of a voltage. They're called electromotive force, but they're not a force, they're a voltage. So if the voltage comes before the current, if the voltage is in front of the current, then I have Eli. In a capacitor, that's the inductor there, there's a capacitor there. So the current is before the voltage in a capacitor by 90 degrees. That's how I know which way to draw the diagram, whether the current or the voltage is in front of each other. Voltage precedes the current by 90 degrees in an inductor, and the current precedes the voltage by 90 degrees in a capacitor. So you haven't had the pleasure of having an iceman or an ice truck or an ice horse, but I have, so I can always remember which comes first. Not the chicken or the egg, it's the ice or the Iceman. So now we know how to get the phase angle for part B, and in part C we want to see if this all works. So in part C we have our phase diagram, and of course, just to make sure you get the same answer, you measure the voltage across the resistor, and it's plotted at the 0 degrees phase angle. And then you add to that like vectors, because these phasors, voltage phasors, add mathematically like vectors. We know all about vector addition from last semester, so we can use that. So we plot the voltage across the inductor at that angle we calculated in part B, took the average of, and we also then plot the voltage across the capacitor at the minus 90 degree angle that we learned in part A. And the total voltage across everything is going to be that value there. So if this all works theoretically and checks out in the lab, you're going to measure this voltage, plot it in a diagram like this at that angle, or at least sketch it in that angle. You can calculate the x and y components here. This is V sub RL, and this is V sub LL. We talked about that a bit ago. And the voltage across the inductor we saw across the capacitor in a pure capacitor, which they all are, is plotted at minus 90 degrees. This is the minus and plus direction given by Eli the Iceman. And so we can get the overall phase angle here, but the question is this total voltage the vector sum, so to speak, of this voltage plus this voltage plus this voltage drawn at these angles, 0, minus 90, and whatever that angle is in part B. So that is the big question. So check that out, see how close you come to your measured voltage being equal to the calculated voltage from part A and part B, from part A and from part B, and also together from part C. That's the experiment. It's pretty simple to do. I would spend, you can do it in 15-20 minutes. I would spend an hour at least doing this diagram, sketching this phasor diagram, and coming up with is this value equal to this value that you measure in the lab and you calculate by your phase angles and your impedance diagrams.